Okay, so in this video I'm going to be doing a quick review of some key things from trigonometry. This is by no means intended to be a comprehensive review. I probably won't do quite as much detail as I did in the lecture, but it's just meant to give you a reminder of some of the most important things that we're going to be needing in the upcoming lecture on trig functions. So, in trigonometry, it's important to think about the unit circle. So this is a circle that has radius 1. And recall that a radian measure for a given angle theta is going to be the distance that we travel around the outside of the circle. So if we have some angle theta like this, then the size of this arc here will be the radian measure of this angle. And so, for example, if we start at the origin, we're at a radian measure of 0. Then there are some key values around the unit circle, like pi over 6, pi over 4, pi over 3, pi over 2 is half, a quarter of a way around the circle. Pi is halfway around the circle. 3 pi over 2 is 3/4 of the way around the circle. And then if we go all the way around the circle, that's 2 pi radians, and then we can keep going around if we want. So you may be used to working with degrees, or maybe you've seen radians before, but in calculus we're going to stick to using radians because they're the most convenient to work with in this setting. So then, once we have the unit circle, we can introduce trig functions. So, given some angle, we see that this line here moving out at that angle hits the circle at some point, and this point is going to have some x and y coordinates on the circle, and we call the x coordinate cosine of theta and the y coordinate sine of theta. So sine is equal to the y coordinate on the unit circle. Cosine is equal to the x coordinate on the unit circle. And so an immediate implication of this is that these two functions, since the circle is radius 1 and their coordinates on the circle, we know that sine of theta and cosine of theta both always have to be between -1 and 1. So in other words, these are bounded functions. Another important point is that sine and cosine are periodic, meaning that sine of x plus 2 pi is equal to sine of x, and similarly cosine of x plus 2 pi is equal to cosine of x. So since there's 2 pi radians in the circle, this is basically saying if we increase our angle by 2 pi, we get back to where we started. And so if we go all the way around the circle, our x coordinate is unchanged. That's why we have these equations, and similarly the y coordinate is unchanged. So that's why we have this equation for sine. So the graphs of these functions look something like this. This is for sine of x, and then we have something like this for cosine of x. So sine of x has zeros at pi, 2 pi, -pi, and so on. Cosine of x has zeros at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. And since these functions are periodic, these patterns just repeat if you keep going further out to the left or the right. So another thing that's important about these trig functions is that since they're coordinates on the circle, if we look at this triangle that they form, we know that the hypotenuse is length 1 because it's a unit circle. We know that the x coordinate, or the x distance, is cosine theta, the y distance is sine theta. So by the Pythagorean theorem, we have the important identity that sine squared theta plus cosine squared theta is always equal to 1. So this is a very useful trig identity. This is really the only one that I expect you to have memorized for this class, at least for the time being. Maybe later in the class some will be useful when we do some different topics. But for the purpose of doing derivatives with trig functions, this is really the only one that I'm going to care about. Okay, so that's some stuff about sine and cosine. There are other trig functions. There's tangent, which is sine divided by cosine. There's cotangent, which is equal to cosine divided by sine, or 1 divided by tangent. There's secant, which is 1 over cosine. And there's cosecant, which is 1 over sine of x. So those are the 6 trig functions. And sometimes you'll also see these things defined in terms of a triangle. So if we label the sides opposite, adjacent, hypotenuse, then sometimes you'll see sine of x equals opposite over hypotenuse, cosine of x is equal to adjacent over hypotenuse, and tangent of x is equal to opposite over adjacent. So these are completely equivalent ways of defining sine, cosine, and tangent. I think if you think about it for a little bit, it shouldn't be too hard to convince yourself that on the unit circle, this is exactly just saying, for example, that sine is the y coordinate, and this is saying cosine is the x coordinate. And then if you look at these two things, it's easy to see that tangent is equal to sine divided by cosine using these definitions as well. So those are the definitions of the trig functions. There are some important values of the trig functions that you should know. So you should know, for example, the value of sine at pi over 6, at 0, at pi over 4, pi over 3, pi over 2, and so on, all around the unit circle. So there's a worksheet posted on the Sakai site which goes through all those values, so I think it's worth just memorizing them. And there are several tricks that can help you to memorize those values. I went through some of that in class. I think I'm not going to spend time on it here, but it is important that if values, you should be able to calculate it relatively quickly. So instead, what I'd like to focus on in the remainder of the video is the inverse trig functions. So these are written as arcsine, that's the inverse function for sine. There's arccosine is the inverse to cosine. There's arctan, it's the inverse to tangent, and so on. And so, as usual with these inverse functions, if sine of x is equal to y, then what the inverse function means is that arcsine of y is equal to x. So basically, sine of arcsine of x is just equal to x. So the sine and the arcsine function undo each other. And so if we look at the graph of sine of x, it looks something like this. And so to get the graph of the inverse function, we want to reflect across the line y equals x. When we do that, we get something like this. And we see that this is not a function because it's failing the vertical line test. So in order to make this a function, we have to restrict the output of arcsine. So specifically to do something like this. So basically we take the values between here and here, and that lets us make this into a function. Now it does pass the vertical line test, so arcsine of x, we take by convention, is always in the interval negative pi over 2 to pi over 2. Similarly, we restrict things for arc cosine. So the values there are typically taken to be in the range from 0 to pi. And then lastly, arctan of x is taken to lie in the interval from negative pi over 2 to pi over 2. And the graph of that function looks something like this. So those are the inverse trig functions. And so the last thing I want to take a look at is how we can simplify inverse trig functions and trig functions applied to each other. So as an example, let's look at simplifying sine of arc cosine of x. So how can we do this? So the idea is that if arc cosine of x is equal to some angle theta, we don't know what that angle is, but we do know that if we take cosine of both sides of this equation, this means that x is equal to cosine theta, and we know that that is equal to adjacent over hypotenuse. So since x is equal to x over 1, we can draw a triangle here. Here's our theta, and the adjacent side is x, the hypotenuse is 1. Then, by the Pythagorean theorem, we know that x squared plus this distance y squared has to be equal to 1. That means y is square root 1 minus x squared. So we can go ahead and label that in our triangle. And now we know that sine of theta, which is the same as sine of arc cosine of x, because arc cosine of x is equal to theta, this is going to be equal to opposite over hypotenuse, and from our triangle, the opposite side is square root 1 minus x squared. The hypotenuse is 1, so we get this for our simplified answer. So if we have a trig function applied to an inverse trig function, it's often possible to write it without any trig functions appearing at all, like in this example. So I think that's everything I wanted to say in this video. So obviously I've skipped a lot of things and not done many examples. This is just a brief overview of some useful trig facts that we're going to be using. And if there's anything in here that was maybe unfamiliar to you, or you don't recall exactly how it works from high school and you want more details, then I suggest you look it up online or come and talk to me.